Okay, in this chapter, we're going to take the information on probability distributions that we worked with in the last chapter and take it a step further. Okay, so I'm just going to read what it says up there in that section 1 comment because I think it's kind of important. In this chapter, we present continuous probability distributions, meaning that in the previous chapter, the binomial probability distribution, Poisson's, those were discrete in that what we did is we found probabilities for exact values. What's the probability that x equals 2? What's the probability that x equals 4, etc.? Okay, now what we want to do is we're going to move into more of a continuous situation, and we're going to look at it in a couple different ideas, and that's what it goes on to say. To illustrate the correspondence between area and probability, we begin with a uniform distribution, but most of this chapter focuses on normal. And remember, we talked about the normal bell-shaped curve and some of the characteristics it's had and the z-scores that go with it. We'll deal more with that as we go. Normal distributions occur often in real applications, and they play an important role in methods of inferential statistics. You don't realize it, but there are normal distributions that take place, every day, all day long. We just don't recognize them as such when we talk about the characteristics that kind of form them. In this chapter, we're going to present concepts of normal distribution that will be used in the remaining chapters of this text. Well, this will be the last chapter that we'll have a chance to talk about. So the first thing they want to talk about is, so they show you the bell-shaped and symmetric curve of a normal distribution. Okay. Another type of curve that we often talk about in this situation is called a uniform distribution. Now, where a bell-shaped curve is, a normal curve is bell-shaped, a uniform distribution is rectangular. Okay? Now, so if this is my x and y axis of a graph, okay, here's what you'll see on a uniform distribution. All of the probabilities have to be exactly the same. So let's say I'm going from 0 to 6. Let's just say we're rolling a die. Okay, something like that. Well, we know that the probability of any one of those events happening, okay, has to be the same if it's a fair die. Okay, so it's a 1 out. So my probability up here is 1 out of 6. Whatever that is a decimal. Okay, now if you add all of the probabilities up, you get 1. Okay, well, in that same regard, the area underneath this rectangle, inside this rectangle, must also equal 1. So the sum of all of the probabilities equals 1, and the area equals 1. The two are tied together. Okay, the two are tied together. And that's also true for a normal distribution. Okay, so when you take a normal distribution that looks like this, okay, then all of these probabilities added together here equals 1. Or, like I said, we can say that the area under the curve is equal to 1. So what we're going to do is we're going to explore that a little bit more. And we're going to use our z-scores. And there's a table that we're going to use a lot as well to be able to look up and find some of those different areas. Okay, but they're not going to be discrete values anymore. Okay, what we're literally going to be looking at is what are areas under a curve, and basically the table that we're going to use is going to show a shaded region, not a specific value. I repeat, it's going to be a shaded region, not a specific value. Okay, so we'll get to that here in just a little bit. But they start off, let me see if there's a couple other things I need to stress, and then we can move on to some exercises. Okay, again, area under, just like when we added up all the probabilities and the binomial distributions. Okay, you know, we added those up, those had to equal 1, so do these. Okay, that's kind of a very important part of this. Okay, and we're going to be working with standard normal curve in this. So everything, the z-scores are already going to be provided for us. Okay, what we're going to be doing in then section 3 is we're going to have to go back to that z-score, and we're going to have to perform some conversions, and then we'll do the same kinds of arithmetic mathematics. Okay, so so there are 3 things they're going to ask you to do. Okay, and I'll show you each procedure has its own set of rules, but they're all very similar. Okay, so I want to be able to find, let's say, for example, I'm going to use my bell curve up here. Okay, if this is, we'll call this x. Well, let's call it z. We're going to start with z values here. This is the z value. Okay, now because it's on the left side here, it's negative, but okay, what we're going to look at is find the probability, okay, of less than z. Okay, find the probability greater than z. And if I have another value over here, let's call this y. Okay, find the and I probably should use, you know, that x is less than z, that x is greater than z, that x is between z and y. Okay, so I'm looking at either the shaded region on the left, that's less than, the shaded region on the right, that's greater than, or the shaded region in between. Okay, so I'm finding areas under the curve. That's going to be the x value that you're looking for. Z is going to be the z value that tells you, that acts as the dividing line where the solutions stop. Okay, so a lot of this is just going to be looking up on a table. Okay, so once you recognize what category the problem fits in, then we can look it up and go. Okay, and I'll kind of explain that in some of the ones that we're going to be doing. Okay, so next thing, in the exercises, the first thing it does is it talks about problems involving uniform distribution. Okay, so for here it says, in exercises 1 through 4, refer to the continuous uniform distribution depicted in the figure shown below. Assume that a voltage level between 123 and 125 is randomly selected. Find the probability that the given voltage level is selected. Okay, now they have to recognize what they're going to give us is the x value. Okay, in a uniform distribution problem, okay, the shaded region is the area of the rectangle, the little rectangle inside the bigger one. And so if I can determine the length and width of that, okay, if I can determine the length and width, okay, then I should be able to multiply them together to find the area, and that area will also be the probability. Okay, so number 2, find it that less than 123.5. Well, here's my 123.5. Okay, lengthwise, or if you call it widthwise, I guess, that's 0.5. Okay, the height is also 0.5. So anything less than 123.5 would be represented by 0.5 times 0.5, length times width. Okay, and that should be 0.25. Okay, so there's a less than problem. Okay, now number 4 is a between problem. So anything between 124.1 and 124.5, okay, from, you have to kind of estimate where that's at, okay, but the width of that band then is going to be 0.4, and again, going all the way to the top is 0.5. So this time I'm going to take 0.4 times 0.5, and that becomes equals 0.20, or just 0.2, okay? So that's what they're asking you to do on those first 4. When you have uniform distribution, okay, you have that rectangle, use the rectangle, find the length and width, multiply to find the probability or the area under the curve, same thing, okay? Down below, they've given us normal curves, they've given us some z-scores, okay? Again, we are to find the area under the curve. Now, what we have to be careful of with these, and it doesn't do a very good job of showing you where the shading is at. So let me check my notes here again, and I'll help pencil those in. Okay, so here's what I'm going to have you do on these. Okay, I want you to find the probability on the left side on this one. Okay, we're going to find the probability to the right of this one. And then in between on these two. Okay, so that's going to be our goal, okay, for these 4 problems. What's the area under the curve, or the probability that depicted by that z-score? Okay, now then we'll take it backwards here on these other ones. So in your packet of stuff, you have a table, okay, and I hope you have the right table. Okay, that table is a table of z-scores. Okay, now you have negative z-scores, okay, on the front side. That should be the front side. Okay, you can see it starts at negative 3.5, and then it goes all the way up till 0, 0. Okay, and then it flips over and starts at 0, 0, and then from there heads into the positives until it gets to 3.5. Beyond that, the numbers are so small that they go beyond our 4 decimal place approximation. Okay, now you'll notice that in this chart you also see some stars, some asterisks that are mentioned by the arrows. Okay, those are some of the special z-scores that we might see in this course, of they represent some special values associated with some confidence levels, things that we would get into in chapter 6. Okay, but so for example on this one, okay, I have a z-score of negative 7.5, and they're shading on the right. So I want to find what's the probability that x is greater than negative 0.75. Okay, so if I look up negative 0.75, okay, clear down here on the bottom, negative 0.75 is 0.2266. Okay, 0.2266. Now, the problem is that value is actually this side of the graph. This is 0.2266. I don't want this side. I want the right side. The table, the z-scores gives you the left side value. Okay, so on number 5, if that's what I wanted, then that's okay. I'd be good. That's not what I want. So how do you do that? So when you're given a greater than symbol, okay, the probability of x greater than negative 0.75 is the same as the probability of 1 minus x is less than negative 0.75. Because remember, the two probabilities have to add to 1 because your probability and your area under the curve are both 1. So if you take 1 minus the opposite, 1 minus the left side, that has to be the right side. So I'm going to take 1 minus point, we said that was 0.2266. So 2266, I get a probability of 0.7734. Okay, so the area under the curve here represents almost 78% of all of the data, and I have a 77.34% chance of being underneath that part of the curve. Okay, so it works for probability and for area. Okay, so greater than problems are always 1 minus the less than of that same value. Okay, we'll look at another one here. The left side, the less than are easy because you look it up, you write it down, you're done. Okay, greater than and between are the ones that require the extra efforts. Okay, number 8. Okay, in this example, okay, I've got two z-scores here, negative 0.9 and 1.6, and I want to find the area under the curve between those lines. Now, remember what the table's going to do. Okay, so I want the negative 0.9. If I look it up in my table, that's going to be this left side. I don't want that. Okay, if I look at the 1.6, that's all of this left side. So to take off this part over here that I don't want, I'm going to use a subtraction. Okay, so first of all, the probability that x is less than, or excuse me, between negative 0.9 and 1.6. Okay, this is what the equation looks like. Okay, that equals the probability that x is less than 1.6 minus the probability that x is less than negative 0.9. Okay, you're going to subtract the two probabilities, the right side minus the left side. Okay, and that will give you a positive value representing the area between or under the curve. So I'm going to look those up. On the positive side, okay, I at 1.6, 1.60 is 0.9452. 0.9452. Negative 0.90, 1841. And the difference of those I get 0.7611. Okay. Now, the other thing we have to be able to do with these is go backwards. What if I give you the area under the curve, okay, and then you're trying to find what z value it came from? Okay. Well, again, this is for you can't do that in a between problem just because there's too many different values that would create that area under the curve, but we can do it for less than, we can do it for greater than. And that's what they're trying to show you on problems 9 through 12. Okay. The value that they give you, okay, is the value of the probability under the curve. Okay. And again, it amounts to this. If they give you the left side, look it up. Okay. If they give you the right side, subtract it from 1 and look it up. Okay. So number 11. Okay. Number 11 says I have a right side of 0.1075. What z-score? Well, the first thing I'm going to do is I'm going to take 1 minus 0.1075. Okay. So when I subtract from 1, I get 0.8925. Okay. Now, since it is greater than 0.5, it has to be on the positive side. So on the positive side of your worksheet, I'm looking in here in the body of this table, not on the sides, and I'm looking for the number closest to 0.8925. You're probably not going to find it exactly. Oh, on this one we are. So 0.8925 is right there. Sorry, hit the pause button accidentally. Okay, so I'm on the positive side since it's greater than 0.8. or excuse me, greater than 0.5, I know it has to be on the positive side, okay? And I'm looking for 8925, which turns out to be right here on my table, 0.8925, okay? Now, if I go out, this is 1.1, and this is, or excuse me, 1.2, and this is 4. So my z-score is 1.24 when you put those values back together. Okay, so if they give you the right side of the curve, subtract from 1, look it up in the body of the text or the table, and then write down the coinciding value. Okay, if they give you the left side, then once you look it up, then that's your answer. Okay, nothing more needs to be done with that. Okay, so the only one that's a left side is number 10. Oh, excuse me. Yeah, let's go back to do number 10 then. Okay, number 10, they give you the left side. So 0.25 is less than 0.5, so that's a negative. Okay, 0.2546, 25. Again, it's part of on the table. That would be negative 0.66. Okay, so be careful. Okay, but excuse me. So it's right here. All I had to do was look that value up in the table, and that was my z-score. Okay, now the next group of problems is more of exactly the same thing. Okay, they give you a different scenario. They say this time we're dealing with a thermometer, but they're normally distributed with a mean of 0 and a standard deviation of 1. Well, that's what a normal distribution is. So they're using exactly the same scenario, and then they're going to give us a bunch of different numbers, and they're asking you to find the probabilities or the area under the curve. Okay, so so let me look at one here. Okay, so less than 1.23. Again, positive 1.23. It says 8907. Okay, so 0.8927. Write it down. Okay, less than, oh, that's all you got to do. Okay, remember, greater than, the first thing you do, you're going to subtract from 1. So number 20, negative 1.96. When I look that up, I get 0.025. Because it's a greater than, I plug that in and I'm going to subtract from 1. Okay, so in that example, okay, this would be 0.975. Okay, and then with the between problems, just remember you want to go from you're going to subtract the two probabilities, but you need to go to the right side first. Okay, you need to go to the right side first. So 5.00, they're going to get into some extreme cases. Okay, they just want to make sure you're reading the table correctly. Okay, 5.00 is greater than 3.5. So according to the table, for anything past 3.5, we're going to use 0.9999. Negative 2.5 On the other side, looking it up, is 0.0026. Oops. 62, sorry. So 9999.0062. And so I get 0.9937. Okay. So that's the gist of this entire section is being able to use those z-scores to find the probability or the area under the curve, okay, for either a less than, a greater than, or a between situation. Okay, so just remember, less than, look it up, write it down. Greater than, look it up, subtract from 1. Between, look them up and subtract them from the bigger to the smaller z-score. Okay. And then the other thing is just being able to work it backwards if you're given the probability. But even that's kind of limited there. So, because you can only do less than and greater than. Same principles apply as before. Okay. So as we go through this, we got to have some special cases as we refine some of these things here. But our next section is going to ask you to take regular X scores and then convert them to Z scores and then do the same thing. So with that exception, next section won't be a whole lot different than this one. So give me a holler if there's something that was misstated or still don't understand. I think you should be able to kind of get through the answers for these based on what we've talked about. So